Have you ever wondered how energy is transferred or why some machines are more efficient than others? The answer lies in one of the most fundamental fields of physics, thermodynamics. It's not just a branch of science, it's the key of understanding how we harness and use energy in everything from power plants to refrigerators. In this presentation, we are diving into two core concepts. The thermodynamic temperature scale allows us to measure temperatures in a way that's independent of the materials used. It's a scale built entirely on the laws of nature. But why is this important? Because having a universal temperature scale helps us accurately analyze and improve energy process regardless of the substance involved. Then there's the Carnot heat engine, often called the most efficient engine possible. It sets the upper limit for how efficiently we can convert heat into useful work. Imagine knowing that no engine in the world can ever surpass this efficiency. That's the power of the Carnot principle. These concepts don't just stay in textbook, they impact real life. They are why we can build better engines, save energy, and even reduce the environmental impact of our technology.
Okay, so brief description on thermodynamic temperature scale and Carnot heat engine. So thermodynamic temperature scale is an absolute temperature scale based on thermodynamics principle. It starts at absolute zero, where molecular motion ceases, and it is measured in Kelvin, ensuring the universal consistency in science. While Carnot heat engine, a theoretical heat engine that operates on Carnot cycle. So this heat engine achieves maximum efficiency by transferring between two reservoirs at different temperature. It consists of two isothermal processes, two adiabatic processes. Though idealized, it sets upper efficiency limit for real engine based solely on the temperature of the reservoir.
Here, we're going to talk about the thermodynamic temperature scale in Carnot heat engine, the Carnot principle. As we know that thermodynamic temperature scale is an independent of the properties of the substances that are used to measure temperature. Here, we're going to talk about the second Carnot principle, where all reversible heat engines operating between the same two reservoirs have the same efficiency. The Carnot heat engines, hypothetically, heat engine that operates on the reversible Carnot cycle. We know a thermal energy reservoir is a big body of mass that's able to absorb heat or give out heat without changing its temperature. So, the only thing that does not change of a thermal energy reservoir is its temperature. That said that we can see if we have a reversible heat engine and it operates between two thermal energy reservoirs, the thermal efficiency is uniquely dependent on the temperature of the two thermal energy reservoirs. Hence, we can write this general equation. To show the relationship, the thermal efficiency and the temperature of the thermal energy reservoir, we see that the ratio of heat at the lower reservoir over heat at higher reservoir. Between two heat reservoir, we can also calculate their coefficient of performance using the temperature of the two reservoir. Hence, the higher the temperature, the higher the quality of the energy.
In this slide, we will learn more about a real life phenomenon that applies to a second law of thermodynamics. Basically, heat transfer happens when energy moves from hot surface to a cold surface. However, concerning to second law of thermodynamics, heat transfer occurs opposite to its nature process. So one of the basic appliances uses in daily life is the refrigerator. When it comes to daily use appliances such as refrigerator, which uses the second law of thermodynamics, where the heat transfer from cold surface to hot surface, it basically uh, requires the external work or external energy to do that process. Refrigerator itself undergoes the thermodynamic cycle, which has four sessions of it, which is evaporation, compression, condensation and expansion. The first process that happens during the thermodynamic cycle inside the refrigerator is evaporation, where the heat will absorb inside the refrigerator. Basically, the heat from the food that we store inside the refrigerator was absorbed. And for the second process, it will be compression, where compression the external work is needed or external energy is required so that the coolant can be compressed to increase the temperature. Along with that, condensation will occur as a third process in the thermodynamic cycle, where it requires the high pressure and heat will release through the condenser coil to surrounding. And lastly, the expansion, where the cooling down process occurs where the temperature drops. So basically, this thermodynamic cycle inside the refrigerator will repeat again and again.
Carnot heat engines operates between a source at 1000 Kelvin and a sink at 300 Kelvin. If the heat engine is supplied with a heat at a rate of 800 kJ per minute, determine the thermal efficiency and the power of output of this heat engine. Based on the questions given, the thermal efficiency of a Carnot heat engine depends on the source of the sink temperatures only. That can be determined from this formula. Thermal efficiency equal to 1 minus low temperature reservoir TL over higher temperature reservoir TH. Since the value of TL 300 Kelvin and TH 1000 Kelvin has been given from the questions, we just need to sub the value of it into the formula. We get 0.70, which is 70% the maximum efficiency of a heat engine. Next, we need to determine the power output of these heat engines based on the definition of thermal efficiency rate of work net equal to thermal efficiency times with rate of heat transfer of heat engines. Just sub the value of thermal efficiency that we obtained from question A and rate of heat transfer that have been given from the questions. The power output of these heat engines is 5060 kJ per minute, equivalent to 9.33 kilowatt.
A Carnot heat engine shown in figure receives 500 kJ of heat per second from a high temperature source at 652 degrees Celsius and reject heat to a low temperature sink at 30 degrees Celsius. Determine the thermal efficiency of this Carnot engine and the amount of heat rejected to the sink per cycle. For the first question, the Carnot heat engine is a reversible heat engine, and the efficiency can be calculated by using 1 minus TL over TH, where TL is the low temperature and the TH is the high temperature. This temperature scale must be in the Kelvin scale. So we get 0.6723. This need to convert into percentage where we get 67.23%. For the second question, the amount of heat rejected QL can be calculated using this formula. QL equals to TL over TH times QH, where TL is the low temperature, TH is the high temperature, and QH is 500 kilojoule. So we get 163.838 kilojoule.
In conclusion, the thermodynamic temperature scale based on the absolute zero ensure universal consistency in scientific measurements, while the Carnot heat engine defines the theoretical maximum efficiency of converting heat into work.